Hello and welcome to all on my YouTube channel JK Academy India. In this video, we will discuss about the parallel operation and the types of the transformer. So, the classification of transformer based on their application. Power transformer. These transformers are used to step up the voltage at the generating station for transmission purposes. Then to step down the voltage at receiving stations. These transformers are large, having the large capacity, generally above 500 kVA, usually operate at high average load, which could cause continuous capacity copper loss, thus affecting their efficiency. To have minimum losses during 24 hours, such transformers are designed with low copper loss. Second, distribution transformers are installed at a distribution substation to step down the voltage. These transformers are continuously energized, causing iron losses for 24 hours. Generally, the load on these transformers fluctuates from no load to full load during this period. To obtain high efficiency, such transformers are designed with low iron losses. Third one is the instrument transformer. To measure high voltage and current in power system, potential transformer PT and current transformer CT are used. The potential transformer are used to decrease the voltage and CT are used to decrease the current up to measurable value. These are also used with protective devices. Now, testing transformers are used to step up the voltage at very high value for carrying out the test under high voltage for testing the dielectric strength of transformer oil. Special purpose transformer may be designed to serve special purposes. These may be used with furnace, rectifiers and welding set. Auto transformer are single winding transformer used to step down the voltage for starting of large three-phase squirrel cage induction motors. Isolation transformer are used only to isolate electricity, the electronic circuits from the main circuit line. Therefore, their transformation ratio is usually 1. Impedance matching factor transformer are used at output stage of the amplifier for impedance matching to obtain output from the amplifiers. Parallel operation of transformer. When the primaries and secondaries of two or more transformers are connected separately to same incoming and outgoing line to share the load, the transformers are said to be connected in parallel. Two single phase transformer A and B are placed in parallel as shown in this figure. This is A and this is B. Here the primary winding of the two transformers are joined to supply bus bar and secondary winding are joined to the load through load bus bar under such conditions. So what is the necessity of parallel operation? When the load on transmission line increases beyond the capacity of the installed transformer, to overcome this problem, one way is to replace the existing transformer with the new one having the larger capacity, but that is augmentation of transformer. And other way is to place one more transformer in parallel with existing one to share the load. The cost of replacing the transformer is much more than placing other one in parallel with existing one. Hence, it is desirable to place another transformer in parallel when electrical load on the existing transformer increases beyond its rated capacity. Sometimes the amount of power to be transferred is so high that it is not possible to build a single unit for that capacity. Then we have to place two or more transformer in parallel. Hence, parallel operation of transformer is necessary when the amount of power to be transformed is much more than that which one can be handled by the single transformer. All the grid substation spare transformer are always necessary to ensure continuity of the supply in case of breakdown. The size of spare transformer depend upon the size of transformer placed in the grid substation. Therefore, it is desirable to place transformer for smaller capacity in parallel to transform the given load, which in turn reduces the size of the spare transformer. Hence, it is desirable to do parallel operation of transformer if we want to keep the spare transformer of smaller size. Now, what are the conditions for the parallel operation? Here we will see the single phase transformer first. So, both the transformer should have same transformation ratio, that is, the voltage rating of both primary and secondary must be identical. Both of the transformers should have the same percentage impedance. If this condition is not exactly fulfilled, the impedance triangles at the rated kVA are not identical in shape and size. Even then, parallel operation will be possible, but power factors at which the transformer operate will differ from the power factor of the load. Therefore, in case the transformer will not share the load in proportion to their kVA rating. Next, both transformers must have the same polarity. Both the transformers must be properly connected with regards of their polarities. If this condition is not observed, the EMF in the secondary winding of the transformers which are in parallel with incorrect polarity will act together in the local secondary circuit and produce the effect equivalent to a dead short circuit. In case of three-phase transformer, the two transformers must have the same phase sequence, that is, the transformer must be properly connected with regard to their phase sequence. If this condition is not observed, it will have the same effect as discussed above when the polarity of the two single phase transformer was not the same. Phase sequence is also checked as discussed above. In case of three phase transformer, the two transformer must have the connection so that there should not be any phase difference between the secondary line voltage, that is, delta star transformer should not be connected with delta delta or star star connected transformer. If this condition is not fulfilled, it will cause a heavy circulating current which may damage the transformer. Load sharing between two transformers connected in parallel. When two transformers have the same voltage ratio and their impedance voltage triangles are identical in size and shape, the condition for which the transformer have the same voltage ratio and impedance voltage triangle is known ideal condition or ideal case. Let E be no load secondary voltage of each transformer and V is the terminal voltage as shown in this figure. The equivalent circuit in which I1 I2 are the current supplied by transformer A and B respectively, I be the total load current lagging behind the voltage V by an angle phi. The impedance voltage triangle of the individual transformer are identical in shape and size and therefore represented by a single triangle VAB with resistive loop resistance drop side VA parallel to load current vector OI as shown in figure. The current I1 and I2 in the individual transformer are both in phase with the load current I and are inversely proportional to their respective impedances. Here two transformers are in parallel supplying I current to the load. First transformer is having I1 current, second one is having the I2 current. Impedance of both the transformer is different, but they are represented by this triangle. I1 and I2 are lagging behind the voltage by an angle phi, and this is the total EMF. E1 equals to E2 equals to E in the secondary side. So the total current I will be I1 plus I2. Now I1 Z1 is equal to I2 Z2. Therefore I1 by I2 equal to Z2 by Z1, and you can find the I1 value from here. Now putting I1 value in this case, we will get I2 Z2 plus Z1 upon Z1, or you can calculate the I2 also. So I1 will be Z2 upon Z1 plus Z2 into I. Multiplying both the side, the common terminal voltage V, we will get VA, means the volt ampere capacity of the transformer. So the capacity of first transformer will be kVA1 Z2 upon Z1 into Z2 upon Z2 into total kVA. When the two transformers have the same voltage ratio but different voltage triangle. In this case, no load voltage of both secondary are equal in magnitude as well as in phase. There is no phase difference between E1 and E2, which only possible if magnetizing current of the two transformers are not very different from each other or nearly the same. Under these conditions, both sides of two transformers can be connected in parallel and no current will circulate between them on no load. Figure shows the equivalent circuit diagram when parallel connected transformers are sharing the load current I, and it represents two impedances in parallel. The impedance voltage triangle is now presented by two triangle VAB. VA dash B having common hypotenuse, that is VB, as shown in this figure. Now you will see the calculation, how it was performed. The equivalent circuit and vector diagram are shown in previous slide. It is seen even when secondaries are on no load, there will be same circulating current in the secondary because of inequality in their induced EMF. This circulating current IC will be E1 minus E2 upon Z1 upon Z2. As the induced EMF of the two transformers are equal, total drop in their respective circuit will be this, and from this we can calculate the current I1 flowing through the transformer 1, similarly current I2. So these are the normal mathematical calculation, you can go through it. And multiplying both the side by V, we will get the kVA rating, and Vi is multiplied by 10 to power minus 3, you will get the kVA rating. Vi1 will give the kVA rating of transformer A, and Vi2 will give the kV rating of transformer V. From this, the relation what we have seen, that kVA ratings are in proportion to their impedances. When two transformers have different voltage ratio and different voltage triangle, the voltage triangle is also different. In this case, the voltage ratio or transformation ratio of two transformers are different. It means these no load secondary voltages are unequal. Even E2 be the no load secondary EMF of the two transformer and Z be the total impedance across the secondary, then the equivalent circuit what you have seen, it is seen that even when secondaries are on no load, there will be some circulating current in the secondary because of inequality in their induced EMF. Similar calculations are given in this, as we have seen in previous slide. So from this you can calculate the current I1, and by putting the value of Z1 and Z2 of both the transformers. Here ZL is the load impedance, the physical interpretation of second term, this I2, is that it represents the cross current or circulating current between the secondaries. The first term, how the actual load current divides between the load. If E1 and E2, the ratio of the currents are inversely as the impedance of the numerical values. So thank you for watching. We will meet in another video. Take care and goodbye.